Hi, I'm Jon McLoone, and as well as working on various projects at Wolfram Research, I'm also Content Director for computerbasedmath.org, an organisation which is rethinking the maths curriculum for the age of computers. So in contrast to some of the other talks in this virtual conference, I want to look at how we can use technology to improve the subject of math, rather than just changing the way that we teach it. So let me start by making two seemingly contradictory claims. First, the maths is more important than at any time in history. It has pervaded once qualitative subjects like zoology and geology. It has driven technical subjects like engineering and physics into levels of detail that were until recently unthinkable. And it has almost completely overtaken subjective decision-making in subjects like finance. More disciplines, more products, more jobs use maths at their core than at any time before. But computation skills have never been less important. While the ability to think mathematically is still vital, the actual, concrete math skills that we teach in schools are becoming increasingly irrelevant. We teach hand computation skills that scale poorly to real problems. We cover maths invented for a classical world, geometry and univariate algebra, but have little or no coverage of maths invented for the modern world. Graph theory, optimization, cryptography, statistics. For generations, students have said, when will I ever use this stuff? But increasingly, they're right. So, what's changed? Well, of course, it's computers. Computers have industrialized computation. Almost every systematic mathematical computation is now entirely automated. And at least in the mathematical world, that automation rises continually to automate the application of a wider and wider classes of problems, taking care of algorithm choices and parameter optimization, making it possible to do more and more sophisticated computation without any special expertise. Doing computation, once a great challenge, is now easy. And the removal of that hurdle is exactly why math has grown to dominate so much of modern life, and to enable much of our technological progress in the modern world. But the rapid obsolescence of many hand computation skills should not be a source of depression for the maths educator. There's more to maths than computation. These external effects that are reducing the need for computational skills are, at the same time, putting great pressure on maths education to deliver more and more conceptual knowledge and conceptual understanding. This is value that our current maths education still delivers, but it delivers it via this proxy subject of hand computation. If we want students to understand how to wield the power of a symbolic model, we can do far better than teaching that by endless practice of expanding and factoring brackets. We should focus instead on ways of getting more directly to the concepts, rather than going through the route of details of the mechanics in order to hope to get to that end. There is also a greater demand for more experience of application, taking real-world problems and using the power of maths to handle them. But real-world problems are complex and messy and not amenable to hand calculation. And even if they are, you can't get experience of many of them when each problem takes an age to solve by hand. Assuming computers will be there to do our computation lets us tackle many more problems and much harder problems, and lets us develop experience, and with that intuition, that hand computation can never deliver. The key here is to remember at every stage that maths is not the same as computation. It's a much bigger subject, and we should see it as a liberation that we are freed from much of the computation, so that instead we can concentrate on the rest of this glorious subject. So what is this wider subject? Well, I'm going to break it down by looking at the process of doing maths, which we see as essentially 4 steps. First is posing the right question, asking, what do I know? What don't I know? What am I trying to find out? What maths do I know that might be relevant? At the moment, students are typically robbed of that by questions that state all of those things before they're allowed to even start thinking. Questions say, here's an equation, here are the values we know, find the value for x such that y equals 0. There's no chance to ask the right questions because everything has been provided. The second step is to take the real world and mathematize it, to turn it into an abstract mathematical representation. And we also need a mathematical representation of what computation we want to perform, and a representation of the goal that we seek. Basically, to translate the real world into the language of maths. The third step is taking the mathematical representation and computing it into a mathematical representation of your answer, tracing those symbols around the page, applying whatever truths and algorithms we know should apply to our math representation, until in the end the required answer is reached. And lastly, we have to translate back from math to the real world. What does the computed solution really mean? What decisions do I take based on the answer? And a big part of this is validation. Is the answer right? Really, validation is closing the loop back round to the start again, as we have to ask the right questions to validate. Things like, how can I test if it's right? What do I know that I can compare the answer to? And we might need to find an abstraction of those and perform a computation in order to resolve the verification question, so we might go around the whole loop again. But here's the crazy thing. We spend 80% of our education time teaching step 3, when that is the only step that computers can do. And that leaves us only 20% of the time to teach steps 1, 2, and 4, where, at least for now, computers are fairly useless. At computer-based math, we think that the answer is obvious. We use computers for step 3 as much as possible, and we use students for steps 1, 2, and 4. Changing the default assumption that you need to be able to do every step yourself before you can use math radically changes the content of and approach to maths education. We think there are only 2 cases where you should still teach hand computation. The first is when it is the most practical way to solve the problem. For example, times tables are still probably the best way to do in-the-field multiplication problems for small numbers. And there are still, for now, a few mathematical tasks where the automation of computation has not yet overtaken human abilities. And for those, it is still practically useful to know how to do the computation yourself. The other case is when it is conceptually enlightening. That is, where knowing how something is computed is the best way to understand what it is that you're computing. But I caution you that you have to be ruthless about asking yourself, why am I learning this? Because we all have classic educations that are hard to let go of. And I've certainly found myself defending a computation on the basis that, well, I learned how to do it and I turned out okay. The default assumption should be that it is left to the computer, unless we can find a really compelling explanation of what hand computing it is teaching us. And even if it is conceptually enlightening, that does not mean that practicing the computation repeatedly to develop skill in it is of any value. For example, I found creating a derivative from first principles quite enlightening. Seeing that a line that I drew on x squared tended to the line 2x as the gap between the points limited to 0, that was kind of interesting. But then I spent a week practicing the approach on x cubed, x to the 4, x to the n, sine of x, exponential, umpteen others, and this didn't really add anything significant, at least in terms of concept. Conceptual understanding is not the same thing as algorithmic skill. Let me be clear about a key distinction. Computer-based math is about a fundamental rethink of the subject of maths, and this is distinct from much of the discussion about using computers in the classroom, which usually has been about how to improve the teaching of the traditional subject. And we refer to this as computer-assisted maths. There's nothing wrong with computer-assisted methods, and indeed, to teach computer-based math well, the best of computer-assisted methods need to be applied. But what I'm talking about in this talk is the changing of the subject itself. So, if we're changing the subject, what does that mean? Well, first we have to think about the curriculum. What content do we teach? What concepts are useful? Which are no longer useful? What skills are needed? How does it key into other subjects? In other words, what context do we give it? Surprisingly little discussion is given to the target outcomes of the subject. In what ways do we expect the student to be changed by studying maths? Have some knowledge of the subject, for sure, but if that were all, then math education would have no more point to it than studying baseball statistics or Klingon. If we don't hone in on the outcomes beyond subject knowledge that we're trying to achieve, then we simply won't achieve them. We need to think through some of the teaching modalities to convey the outcome, and of course there's no point rethinking the subject without changing assessment. Computer-based math will not, on its own, help students pass the current standardized math tests. In fact, the opposite, since we feel that many of the tests are testing irrelevant skills that we don't intend to teach. Well, let's look at those in turn. We'll start with the curriculum. Maths holds a uniquely powerful position as being essentially the only subject, apart from local language, which is taught everywhere to everyone. And it holds that position because it is uniquely useful in the real world. So our start point, we believe, has to be the real world. And so we're constructing everything in a problem-centric way rather than a mechanic-centric way. If you look at typical lessons or chapters or sections of textbooks, they usually start from the mechanics. Content is organized around the process. It's ordered according to computational dependency and computational complexity. And any attempt to give context arrives at the end in a form of contrived word problem wrappers for practice exercises that are simply practicing the mechanics again. In a problem-centered approach, we want to start with real problems that have context naturally, that might actually be interesting to students. At least some of student disinterest in maths, and even some of students' maths anxiety, stems from their inability to understand what this important subject is for, and this shouldn't be obscured from the students. One lesson we rapidly learned was not to try and invent contextual problems to illustrate specific pieces of maths. The result always felt contrived, was rarely rich, and hardly ever open-ended. And it meant that we naturally reinvented the classical subject. One criterion for deciding what the curriculum should include is simply seeing which areas of maths you encounter when solving problems. Take an open-ended problem that seems interesting and ask yourself, how would you go about solving it? Solve it for yourself and see what maths emerges. You quickly realize that some concepts that were once central rarely come up, either because they've been superseded by newer approaches or because they were only ever useful on toy problems. This leads me to the next lesson we learned. Do not limit yourself to toy problems. Conventional wisdom always seems to have it that you should find the simplest possible problem to illustrate a maths concept. But that takes away all chance of learning about breaking complex problems down, about uncertainty and validation. And, frankly, most kids can see through it, defeating the opportunity to really make them feel that the subject does something useful. Now, there's nothing wrong with taking an open-ended complex problem and looking for a way to simplify it until it becomes amenable to solution. But then at least there can be a real discussion about whether the simplifications are reasonable and how they might affect the result. But always start from the real question. Okay, let's talk about the outcomes we want to achieve from this education. On top of my list is confidence to tackle new problems. There was a time once where one learned maths to be able to solve already solved problems, but today that's for programmers to fill the need once and forget. Most of the rest of the outcomes support this first one, because in the end this is what we need as students to be able to do, take the skills they learn and apply them to tackle new problems. The ability to abstract is a core skill. That, after all, is the central power of maths, to find abstract representations for which there are known rules of behaviour. If you can't abstract, then you're just a computer. Planning and managing the process is a real-life skill. What do you do if the answer is wrong, or it's going to take 100 years to compute, or you forget a step? Things go wrong, and you need experience of fixing them. Don't try and isolate your students from these real-life problems. I said earlier that verification and critiquing is a key skill. One common question I get about computer-based maths is, if students trust the computer, how will they know if the computer's got it wrong? Well, yes, I say, how do they know? Well, my traditional education gave me exactly 3 ways of knowing. One was check your work. The second was the question gave you the answer. It said something like show A equals B, and when you got to B, you knew you had full marks. And the last was that the answer would be something nice, like a half, or x plus 1. Then it was probably right. But if it formed a piece of algebra that took more than a line to write down, it was probably wrong. Well, those methods are no good anymore. In the real world, you can't check your computations by hand if you're optimizing 100,000 equations in the model of a bridge. And you probably won't get a neat, simple answer. we need to teach students how to develop verification strategies. Strategies that will stand up to real-world problems. Communication is also a part of math, both in a one-way sense, creating reports and papers and knowing how to use visualization effectively, but also in collaboration. And then, finally, we reach concepts and tools. But even here, the tools are secondary. Let's take, say, standard deviation. It's a perfectly valid tool that a student should be aware of for measuring data dispersion. But what's really important is the concept of data dispersion. And students should equally be aware of the other tools for quantifying it. Interquartile range, mean deviation, median deviation, there's more of them. Of course, these weren't as useful before computerized data handling, but now they're just as valid as standard deviation. And finally, through experience of application, we want to achieve an instinctive feel of maths. Perhaps that's a bit of a vague thing to say, but is that gut feeling that tells you whether an approach is likely to succeed, where to look for typical problems, and which allows you to apply estimation to the inputs and in helping validate the outputs. We put effort already into giving that skill to students for arithmetic, but not much beyond that. The key to this is experience. Okay, teaching modalities. I don't have time to look at specifics, but the key here is that once you have a set of outcomes, your teaching or learning methods have to target them. If we want students to build confidence to tackle new problems, then we need to allow some degree of open-ended exploration, so that they get used to going beyond the safe haven of the original question. Open enough that they can discover something, sometimes open enough that they get a little lost. If we want to center around real-world problems, then they should get used to using powerful tools. And we need activities, whether they're collaborative exercises or competitions, which cause students to exchange ideas. Just like the curriculum itself, we think assessment needs to reflect real life. For a start, it needs to use computers. And since the outcomes that we're testing have little to do with factual recall, that should probably include access to reference information. Tasks, again, should be open-ended, and don't necessarily need to have a right answer. A sound approach, using sensible application of concepts, well communicated and carefully validated, is to be valued more than the ability to apply an algorithm. History has repeatedly been changed by automation, from the invention of agriculture to the Industrial Revolution, and each time, embracing it has moved civilization to a higher level, and each time, removing the mechanics of a task has allowed more focus on the real aim of that task, allowing us to achieve that aim better. People don't learn how to machine pistons before they're allowed to drive, or how to develop film before they can use a camera. By standing on the power of automation, we can instead spend our time driving and photographing, and in the case of maths, we can spend our time learning to be first-class problem solvers instead of third-rate computers. Some assume that this takes something away from the subjects of math, but I believe the opposite. I believe that what we're proposing makes the subjects of maths at the same time more practical and more conceptual. And surely it's rare for a change to push in both directions at the same time. Well, thank you for listening, and if you bear with me, I will now take some questions.